You know, whenever you step onto a modern airliner, you're stepping inside one of the most complex and honestly safest machines humanity has ever created. And while we see the obvious stuff, the wings, the seats, there is this entire hidden universe of systems all working together, all designed for one single purpose: to be incredibly safe. Today, we're going to pull back one of those panels and look at a system you've probably never even heard of.
So let's just jump right into the big question. Picture this, you're cruising at 30,000 feet. What happens if one of the plane's main power plants, an engine-driven generator, just stops working? What happens to all the screens in the cockpit, the flight controls, the lights in the cabin? It's a pretty scary thought, right? But it's a scenario that engineers have obsessed over for decades.
Well, here's the short answer. The lights stay on. In fact, if you were a passenger, you would have absolutely no idea anything had even happened. And the reason why is this brilliantly simple, yet unbelievably tough piece of engineering that's designed to solve this exact problem.
To really get this, we have to think about an airplane a little differently. Don't think of it as a single vehicle. Think of it more like a tiny, flying city with its very own electrical grid, complete with two independent power plants. So, on an aircraft like the Atr72, each of its two engines has a powerful DC generator attached right to it. These are the power stations. You've got engine number 1 powering generator 1 and engine number 2 powering generator 2. They are the absolute heart of the plane's main electrical system. Okay, so how does that power get to where it needs to go? This is where it gets really smart. Normally, each generator powers its own separate network. These networks are called buses, so generator 1 is in charge of DC bus 1, and generator 2 is in charge of DC bus 2. It's like having two totally separate power grids running side by side, completely isolated from each other. And just to give you a sense of the scale here, the plane actually has several different electrical systems running all at once. You've got AC systems for sensitive electronics, other systems for heavy-duty stuff like de-icing, but that safety net for the main DC system, the one that keeps the plane flying, is just so clever. So let's stick with that one.
And that entire safety net, it all comes down to one absolutely crucial component. It's truly the unsung hero of the electrical system, a device called the Bus Tie Contactor.
And hey, you don't have to take my word for it. This quote from the Atr72 training manual says it all. The second a generator fails, a computer called the Bus Power Control Unit, or BPCU, instantly tells something called the BTC to close. And the most important part? All these operations are automatic. The pilots don't have to lift a finger. So what exactly is this BTC? Well, at its core, it's a huge, incredibly fast, computer-controlled switch. It's tucked away in an electronics rack, and its whole job in life is to be that invisible bridge. When everything's working fine, the bridge is up. The two sides are separate. But the instant one side loses power, the BPCU throws the switch, the bridge slams shut, and it connects the two networks. So how does this automatic save actually play out in real time? Let's walk through the whole sequence, which happens in 4 lightning-fast steps. All right, here's the play-by-play. Step 1, you're in normal flight. Everything's humming along. Generator 1 is feeding its network, generator 2 is feeding its network, and that bus tie contactor, the BTC, is open. Step 2, generator 1 fails. An alert pops up in the cockpit, and its whole network goes dark. Step 3, instantly, and I mean instantly, the system detects the failure and commands the BTC to close. And bam, step 4, the bridge is complete. The one good generator is now powering the entire aircraft, and all essential systems are back online. It's a totally seamless, automatic save. Now you might be thinking, okay, I get it. There's one super important switch, the BTC, that acts as the guardian for the main flight systems. But here's the thing. This philosophy of automatic backup is so important in aviation that the story doesn't end there. There's more than one of these invisible guardians on board. For that main DC system we've been talking about, the one that powers the really critical stuff like flight instruments and computers, there is one primary bus tie contactor. It is the hero of our story, so far. But remember that other system we briefly mentioned, the AC wild frequency system? Think of this as the electrical grid's heavy lifter. It runs the really power-hungry jobs, like the heaters that keep ice from building up on the propellers and wings. That's obviously critical for safety too, so you can bet it needs its own bulletproof backup plan. And to protect this separate high-power grid, the Atr72 doesn't have one, it has 2 additional bus tie contactors. They do the exact same job. If one of the AC power sources fails, they automatically close the gap and let the good one take over the entire load.
So let's do the final tally. We have 1 BTC for the main DC system, and then we have 2 more for the heavy-duty AC wild system. That gives us a grand total of 3 bus tie contactors all standing by, ready to act as a team of invisible guardians, making sure that electrical network stays up and running no matter what.
You know, this whole system is just such a perfect example of a core principle in aviation design, engineering for the what-if. It's a philosophy of building in layers upon layers of smart, automatic redundancy. Because when you're 30,000 feet in the air, you can't just pull over to the side of the road.
And this really shows you just how versatile the BTC is. Its main job, of course, is that automatic redundancy in the air. But it also lets pilots manually separate the grids if they ever need to for some reason. It even manages power on the ground, so a single cart can light up the whole airplane. Every single one of its functions is about creating a fail-safe design, where one little problem is always contained and never ever becomes a big one.
It's just an incredible piece of engineering, working silently in the background, keeping flight safe. And it really leaves you with something to think about, doesn't it? As you go about your day, what other invisible safety systems, born from this exact same philosophy of redundancy, are quietly working all around you, just to keep you safe?